Alright guys, I'm back with our Ka problem, part 2. In this part we're going to look at D, E, and F. So let's look at part D. This is the part that's asking you about the percent dissociation. Well, what's that percent dissociation? The percent dissociation is the percent of your acid that actually separates. So you're going to take your conjugate base, C3H5O3, and we're going to put that over the concentration or the moles, whichever you have, of your original acid. And you multiply that by 100 to get your percent. So we found that in the last part when we did that we got 3.03 times 10 to the negative third for the concentration of your conjugate. And you had an original concentration of 0.666 molar for the acid. If we multiply that by 100, we get a pretty small percentage. 0.455% is a percent dissociation. And our 5% rule, we're basically saying that that number is less than 5%. Now, if that is true, it's okay to make that approximation with the, assuming that that x was 0 on the bottom of our equilibrium expression on the last part. And so it's fine. In this case, it is that. Now, if it wasn't less than 5%, in the last one we did, we would have to do some successive approximation, and I'll do one to show you how we can do that later with a KB problem. Okay, so that just gives us our percent dissociation. Part E asks us to find the pH. So hang on one second, let me get rid of this background. Okay, so in part E we're looking to find the pH of our solution, and the pH is the negative log of the hydronium concentration. So there's really two things that you have to realize here. First of all, you have to realize that in an earlier part we had already found the concentration of our conjugate, the C3H5O3, and that is equal to the concentration of your hydronium, right? Because of our balanced chemical equation, if I just pop back to that, looking at the balanced chemical equation, we know that these two, x and x, these two quantities have to be the same in a solution that we added this acid to. That's all that we added. Stoichiometry tells us that they're going to have to be equal. So coming back to this, we're going to take the pH, right? To get the pH, we need the negative log of that hydronium concentration. Well, we've already found that by finding the conjugate base concentration, which was 3.03. So the negative log of that 3.03 is going to give you a pH of 2.5 times 10 to the negative 19. I'm sorry, let me change that. It's 3.03 times 10 to the negative 3. I left that off, our power of 10. And that's really important. If we're looking at a concentration, 3 times 10 to the negative third is between, right, 10 to the negative 2 and 10 to the negative 3. Well, our pH should be somewhere between 2.0 and 3.0. In this case, it happens to be 2.5. Sorry, this is 2.519. And I'm leaving that 2.519 as 3 significant figures. Only the numbers after the decimal in a pH are significant, because the 2 here just basically tells us the power of 10. The 3 after are the ones that are going to be significant. So that's showing this number, expressing it to 3 significant figures. Okay, and let's just tackle this last part of the question. This one asks us to look at the structure. You're given the structure of the acid. So you're given lactic acid. We see that it's a 3-carbon acid. The formula was given to us before, but not the structure. So now we're looking at the structure. We see that there's a 3-carbon chain, and you are asked to identify which one of these hydrogens is the one that comes off. So which is the acidic hydrogen? So you have some choices. Is it the one here, right, in this sort of methyl group that's attached? Is it here where we have an OH, right, that hydrogen? Is it this hydrogen here that's connected to a carbon? Or is it this hydrogen here that's connected to this oxygen? Well, identifying the one that is the acidic one is from this structure, COOH, right? This is the one that's going to be your acidic hydrogen, which is going to be this one right here, looking at the acid. So this part of our structure, I'll highlight that. This part in here is the organic acid section, the COOH group. So the only one that's actually going to behave like an acid is this hydrogen right here. So that's the one you should identify. All right, guys, I'll be back in the next part with KB problem.